Hello everyone, welcome to the next lecture in the course Remote Sensing Principles and Applications. We are going to continue with the topic of remote sensing systems and image acquisition where we left from the previous lecture. In the previous lecture, we saw different mechanisms or different ways in which data can be collected from satellites in near polar orbit. Some of the methods are line scanner, whisk broom scanner, push broom scanner and two-dimensional array type of detectors. We also saw a special case of how data will be collected in hyperspectral sensors and so on. Today we are going to start with data collection from satellites in geostationary orbit. So, in geostationary orbit, essentially the orbit or the satellite is much farther from the earth's surface, like something around like 36,000 kilometers away from the earth's surface. The satellite will be aligned along the equator. So, in the previous case near polar orbit, earth is here, satellite will be moving like this from north to south. In geostationary orbit, that means satellite is placed along the equator and the satellite will rotate the earth at the same speed of the earth. That is, as the earth is moving like this, satellite also will move at the same speed. So, essentially satellites are launched into such geostationary orbits when we want to observe the same part of the earth continuously, essentially for communication purposes or meteorological purposes and all. We need to observe same part of the globe without any break. So, for such applications we normally put satellites in the geostationary orbit. So, the satellite will be seeing the same spot on the earth. As the earth is rotating, satellite also will be keep on rotating. So, that there will be like same place will be imaged continuously without any time gap. In the previous case, like in the near polar orbit, satellite moved like this, earth rotated like this, and there was like also some sort of scanning mechanism involved which collected a two-dimensional image, like line by line the image was built either using a scanner or using a push broom array, push broom type of sensor. So, line by line the image is built. As the satellite is moving, each line will be built, so the entire image will be formed. In this case, when satellites are in geostationary orbit, there won't be any sort of relative motion because satellite will be keep on looking at the same spot of earth. There will be no relative motion of satellite with respect to earth. It will be, they will look stationary. Like if your eyes have the capacity to look at a geostationary satellite, it will look stationary for our eyes. That is why the name geostationary. It will be stationed at one point. So, it will appear continuously there. There is no relative motion between earth and the satellite. In such cases, in order to build a two-dimensional image, there should be a 2D scanning mechanism. That is, the detector element should have a scanner which scans in both north-south direction and also east-west direction like this. So, first the scanning will happen like this and scanning then will happen like this in this direction. So, the scanner will essentially do a two-dimensional image collection. That is depicted in this particular figure. You can see like there is like a scanning element which scans in both north-south like this from top to bottom and also east-west. This east-west scanning can be done in two ways. The scanner itself can move two ways, that is, say for example there is like a scanner attached. Let us assume it is scanning like first it scans in this direction like in the north-south. It looks in the top, scans one line, then comes scans one line like this, or it can move like this and then slowly it can move like this. The scanner itself can move in two dimension, up down, left right and so on, like this it can move. Or in some satellites the east west movement is provided by spinning the satellite along its axis. Like if the satellite is moving like this, that will be like a satellite axis. Around this axis the satellite will be made to spin, that is to cover the east west direction the satellite will be actually spinning. So, what it will happen, the scanner will be there, So, when as the satellite does one spin, the scanner will scan one line. Satellite will rotate. Now the scanner may start from the northernmost point, it may look like this. Satellite will spin, one line is collected. Satellite will rotate, come back again. By the time the scanner would have moved one line down or one row down, then it will collect. Satellite will spin, second line is collected. Now the scanner will be again brought down like this. So, line by line image will be collected by spinning the satellite. The scanner will move along the latitudes, like from north to south, the scanner will move slowly. By spinning the satellite, east west scan will be established or it will be carried out. This is one way. There is a satellite called MSG Savory, which is the satellite will spin, collect the data. On the other hand, some satellites will not spin, because spinning again it involves lot of energy. The satellite has to come exactly to the same orientation, lot of things are there. So, as I said, whenever there is a mechanical movement, it is always problematic. So, some sensors or some satellites will have a 2D scanning mechanism. The scanner itself may scan both east west and north south like this. It will scan maybe one line, then the scanner will come to the next line, scan east west, third line, scan east west and so on. Like this, image can be collected in 2 dimensions for satellites in geostationary orbits. Now we have seen how data is being collected, the simple mechanism of data collection. Next we are going to enter into the important concept of spatial resolution. Like in the beginning of this particular topic, I told you each sensor has 4 specific characteristics: spatial, spectral, radiometric and temporal resolutions. These 4 will define the data collected by the system and also for which applications the data can be used. Everything will be defined by these 4 characteristics. So, now we are going to start with looking at the concept of spatial resolution. Before we move on to the explaining what spatial resolution is, we will first see a simple geometry of how Earth is being perceived by one detector element within the sensor. So, this is, let us assume, one detector element within the sensor. The width of the detector is W. Let us assume the width is, it is in the form of a square with the width W on both the sides. This will be like the optics element, and the distance from the focal plane where the detector will be located and the optics, the first point where the light from Earth enters, is focal length. So, F is focal length. Now, even our cameras has like a focal length or focal distance, right? Focal distance we can say, relating the distance between the center of object point where the light first enters the system to the point where the detector elements are kept. So, this is focal length F. And so, based on the focal length, each detector element will have like a small angle subtended, that is, now I am drawing it in 2 dimension. Let us say this is like width W of the sensor, this is the point the optical point O, and this is how, this is focal length F. So, whatever light ray coming in from the ground within this particular angle will be focused on to this particular detector. This is not a 3D angle, this is not a solid angle I am talking about, I am just talking about a plane angle in 2 dimensions, because like it is a square element, we are assuming it as a square element. So, essentially it is like it will have like a one solid angle in the, what to say, in this direction, and sorry, one plane angle in this direction, one plane angle in this direction, the angle will be same. So, we are talking in terms of like a plane angle. Okay. So, this is one side of detector element, this is the point O, this is focal length F. This angle, maybe we can label it as theta, is known as the IFOV, instantaneous field of view. So, what this IFOV defines? The IFOV is actually determined by two parameters. One, the detector width, how wide or how small the detector element is, the physical size of the detector, maybe in the order of few micrometers, and what is the focal length of the system. These two will determine this angle IFOV. So, what essentially it does, now the satellite is being put to space, let us imagine. Now, the detector is in space observing Earth. So, whatever the angle was there inside the system, this angle IFOV, the same angle will be there on the Earth surface. Each detector element will have the same angle on the Earth surface, and whatever energy coming in from that particular 2D angle, like if it is a square, it is like one angle this side, one angle this side. It is like if you imagine like a plane angle on all directions, you will complete like a square, right. Please imagine it in your mind. So, essentially whatever the energy within that particular IFOV will be reaching the detector element, that particular detector element. So, the IFOV will determine the angle from which the energy incoming will be collected by the sensor, and this IFOV is determined by the detector physical size of the detector, like one side size. If it is a square, it is like one side size, and the focal length of the system. So, IFOV is equal to 2 tan inverse of W by 2f, where W is the physical width of the detector element, f is the focal length. So, here A tan means I mean tan inverse. Okay, so this is the IFOV. So, IFOV means the angle subtended by the detector in its focal plane or in its optics assembly, we can say like optic point. From there, what is the angle subtended by the detector, that is this particular angle. From this point O, what is the angle subtended by one side of detector. So, essentially if you put the same angle in all directions, you will essentially get a square element. So, then the satellite is launched to space. Each satellite will have a characteristic orbital height. Some satellites are put in height of 700 kilometers, some satellites are put in the height of 400 odd kilometers and so on. So, that determines the orbit height. So, now based on this IFOV angle and based on the orbital height, each satellite will have a ground area to be seen by each detector element. That is, let us say the IFOV is looking like this. Okay. So, sensor is on the top. So, IFOV is looking like this. Okay. So, as you increase the height from the ground, so if the IFOV is like here and if you like increase the height of the satellite, essentially the same angle will subtend a larger area. So, what essentially it means, first I told you IFOV means whatever the energy that is coming in within that particular angle will be observed by that one particular detector element. Now, depending on the orbital height, if you take into account both this IFOV and the height of orbit, we will be able to determine the ground area covered by each detector element. So, that is given here in this particular formula, and you can see it in from this particular diagram. So, this angle is IFOV. So, based on the IFOV and this orbital altitude h, that will determine what is the ground area covered by each detector element. So, if there is like a detector element W here, there will be like a corresponding value on this particular side based on the orbital height. So, this ground coverage provided by each detector element is known as GIFOV, ground projected IFOV. So, ground projected instantaneous field of view. So, for that particular corresponding IFOV, if you multiply with the orbital height, you will be able to determine the ground area or distance in the ground covered by that small detector element with a width of W. So, if the width is W in one direction, a corresponding distance will be covered in the ground based on the orbital height. Similarly, there will be like another width in the say width W in this direction. Now, it is a square element, there is another width W. So, the same distance will be covered in the another direction also. This, if you take this as x, that is in y direction. So, it will form like a square for the 4 sides. So, two terms we introduced now, one is IFOV, the angle subtended, the plane angle subtended by the detector element on the ground, which is determined by the physical size of the detector and the focal length of the system. Based on this angle and based on the orbital height h, we can determine what is the ground distance covered by this particular detector element for each side, and that ground distance covered we call it as ground projected IFOV or GIFOV. So, the formulas of both the things are given here. So, IFOV is equal to 2 tan inverse of W by 2F. Similarly, GIFOV is equal to 2H tan IFOV by 2. It is like a simple geometry you can like work upon. Let us say this is like detector element W, this is like a perpendicular bisector, this is the focal point F. Essentially this is the IFOV, say let us assume IFOV is equal to alpha. So, this is W by 2, this is F. So, tan of alpha by 2, I am taking one particular triangle. So, where half of alpha I am taken. So, tan of alpha by 2 is equal to opposite side W by 2 divided by adjacent side W by 2F. I am interested in getting alpha, IFOV is alpha, I have labeled it as alpha. So, alpha is equal to 2 tan inverse of W by 2F. Extremely simple geometry. Similar kind of geometry you can build for determining GIFOV, 2H tan IFOV by 2, you will get the same thing. But just one assumption we are making here is, for the sake of simplicity, we are assuming the detector as like a square element and also the earth as like a flat horizontal surface. Earth is not a sphere anymore, earth is not undulating anymore, it is a pure flat horizontal surface, and we are considering the detector element as a square in order to get these two equations. They are like simplified representations of what is happening in the satellite. So, just imagine, remember always one point, whatever energy coming in within the GIFOV, like the area covered by GIFOV, will be collected by one detector element and will be averaged out and stored as one single value. Say for example, say if a detector has a GIFOV of say 1000 meters. So, essentially 1000 meters by 1000 meters, that complete square will be observed as one single point in the remote sensing system, and whatever energy that comes out will be collected as one single point and averaged out and stored as one energy term inside the detector element. So, energy is averaged out within GIFOV. Next important thing we are going to see is what is known as a field of view. Here we first talked about one single detector element, what is the angle covered by one single detector element, what is the ground covered by that single detector element, IFOV and GIFOV. But I also told you that we will be collecting information for a broad range, for a broad distance on the ground. So, there will be like a scanner which will scan a certain angle. So, rather than each detector just collecting data from it, now it covers a wide track of ground in the across track direction. Or if you talk about push broom sensors, there are like say 1000 odd detectors in each row. They will be collecting energy from say 1000 odd pixels or 1000 odd GIFOVs on the ground simultaneously together. So, for each sensor, what is the total ground area covered in one go in the across track direction? That is what we are going to see now. Let us say this is the system, a scanner system. Let us, for simplicity, let us say this is a scanner. So, the scanner is present inside, and this is like the nadir point. So, it is like from here to here, it is scanning in the 2-dimensional plane. See, this is nadir. So, scanner starts from here, moves like this towards the nadir and moves away, stops here and keep on oscillating. So, this is like if you take it as a scanner. So, this particular angle what is subtended by the full scan along one line, we call it as FOV, field of view. So, the field of view will determine what is the angle covered by the scanner. Or if you have a push broom sensor, let us say we have this many, say some n number of detectors in the across track direction. This is the across track direction. This is not focal point F, this objective point O, this is the focal length F. Earlier when we talked about one single detector element, we calculated IFOV, that is from this point objective point O, what is the angle subtended by one detector element. Now if you are having a push broom type of sensor, let us say you have n detectors in the across track direction, what is the total angle subtended by this entire detector element? Say if you have 100 detector elements in the across track, what is the total angle subtended by all these 100 detectors together on that single point of your optics is known as FOV, field of view. That will determine the total angle subtended by the entire sensor element on the ground at a time. If it is a scanner, the angle is determined by what angle the scanner rotates. Say for example, say modus, it has a scanning angle of 55 degrees. So, from nadir 25.5 degrees this side, nadir 25.5 degree this side. So, it will scan like this 27.5 degrees, 27.5 degrees. It will cover 55 degrees by its oscillation, it is kind of like a scanner. On the other hand, if you take a push broom type of sensors where you have n number of detectors in the across track, the total angle subtended by this n detectors from that particular point O point, that the objective point O, that angle we call it as FOV. And if you take this FOV and associated with the orbital height h, that will give us the total ground area covered by the sensor in one go in the across track direction. That is, say a scanner is scanning like this, based on the angle it scans and based on the orbital height, there will be like a definite width of ground covered by one scan line. So, one full scan line here for the 55 degrees, it may cover certain distance on ground. For modus it is 2300 kilometers. One scan will cover 2300 kilometers totally. Similarly, Landsat will cover 185 kilometers. This distance covered by one scan on the ground is known as swath width, or another term is GFOV, ground projected FOV. So, here I have given it is ground projected FOV, or we also call it as swath width. That will determine the total ground area covered by the satellite in one line in the across track direction. So, this will essentially determine if a satellite collects one line of image, what is the exact ground distance of that particular one line, okay, that is swath width. So, the swath width will be like important parameters in order for us to understand the data collection from satellite. So, as a summary, today what we have seen in this particular lecture is we have seen how data will be collected by satellites in the geostationary orbit, and also we have got introduced to 4 important terms: IFOV, GIFOV, which relates to single detector element on the space related to single detector element, and we also came to know about FOV and GFOV, field of view and ground projected field of view, also known as the swath width. So, just as a summary, the swath width is given by this particular formula: GFOV is equal to 2h tan FOV by 2, very similar to IFOV. The geometry is one and the same, we can always relate it with the IFOV geometry, it is very easy to derive this. So, this particular equation will tell you how to calculate the swath width of the sensor. With this, we end this particular lecture. In the next lecture, we will try to explain what is meant by spatial resolution. Thank you very much.